Alright, this lecture will be on section 6.1, which is about inner products, lengths and orthogonality. The idea is to extend the notion of lengths that you probably know from calculus to general Rn, where Rn is the space of dimension n. So the actual definitions are fairly simple, and this is, even though it's section 6.1, so it follows chapter 5, it's in some sense a more elementary topic. Now we will start with definition of dot product. So given two vectors, suppose V is a vector V is a vector V1 to Vn, and W is a vector W1 to Wn. These are vectors in Rn, and the inner product of V and W is, so sometimes this is called dot product. So you put a dot between these two vectors, and this is a scalar which is equal to V1 times W1 plus V2 W2 plus Vn Wn. So essentially you multiply these vectors coordinate-wise, and then you add everything. Alright, so a slightly different interpretation of the same can be given by saying that this is a matrix multiplication. So is a remark, not really an important one, but V dot product W is the same as saying matrix product of the transpose of V with W. Okay, so this here the multiplication is the matrix multiplication. So V transpose will be this vector Vn, and then you multiply this by W1 Wn as matrices. So this is 1 times n multiplied by n times 1, and you get 1 times 1 matrix, which is of course is a scalar. It's the same thing as saying it's a scalar. Now I'm pretty sure that given any two vectors you can compute this very easily. This is not a difficult concept. But let's do an example. So, example V, suppose it's 1, 0, 5, and W is minus 2, 1, minus 3. So these are vectors in R3. And then the dot product of these two vectors will be minus 2 times 1 plus 0 times 1 plus 5 times minus 3. So maybe I should have written this as 1 times minus 2 the order doesn't really matter. So then you will get -2, -15, and this is -7. All right. All right. Some properties of the inner product. They are all certainly quite simple properties. One is, of course, B times W is the same as W times B. So this operation is commuted, but that is obvious. Two, if you take V1 plus V2, so you have two vectors, and you add them and then take the dot product, it will be the same result as first computing the dot product and then adding them. Alright? 3, if you multiply a vector by a scalar and then take the product, it will be the same as if you multiplied these two vectors first and then multiplied by that number. So C is a scalar. Okay, and finally, for V times V is never negative. This is because if the coordinates are given by, so this is equal to V1 squared plus V2 squared, where these are the coordinates of V, Vn squared, and because we're adding squares, all these numbers are positive. So then you get that this is not a negative number. You can get 0 if all VI's are 0. So that's kind of a continuation of the same. V1, VV is equal to 0 if and only if the vector itself is the 0 vector. So all its coordinates must be 0. Alright. Now at this point I would stop and ask if you have questions, but I'll continue. Now this inner product is related to the length of vectors. And let me motivate what's going to happen by recalling how you compute the lengths in R2. Suppose you want to compute the length of this vector. So you are given a vector V, and this is x1, x2. This coordinate is x1, and this is x2. And we want to compute the length of this line segment, but this is usually denoted by the symbol. So two straight lines, and then you write V. Now, how do we compute this? By the Pythagorean theorem, we know that this is equal to the square root of x1 squared plus x2 squared. So the length is given by this formula. Right? And we can then say that V is given by the dot product of V with itself, and then you take the square root. Alright, so that's the length in R2. And we take this part as the definition of length in Rn. So if you're given V, it is V1 Vn vector in Rn, then the length of V is a definition is the square root of V dot product with itself, which is just the square root of V1 squared plus Vn squared. Okay, so an example. Suppose you are given V 3 minus 1 minus 2 in R3. So then its length is 3 squared plus minus 1 squared plus minus 2 squared. And this is equal square root of 9 plus 1 plus 4. So this is square root of 14. The length sometimes is called also the norm. So norm of V, this is the same thing as length. But these are equivalent concepts. Now, one thing that you expect from the length is the property that if I multiply my vector by some number, its length will increase or decrease by that number, depending whether the absolute value of the number is larger than 1 or less than 1. So, and this is easy to check. So observation, C is a number and V is a vector, then CV, this is simply equal to CV1, CV2, CVn. And if we compute the length, this will be CV1 squared plus CVn squared, which is equal to C squared, and then you have V1 squared plus Vn squared. So I open the parentheses and then take out C squared out. I will get this, and then you get the absolute value of C. So note that it's not just it's not C, but the absolute value of C as a number. So if it was minus 2, then the absolute value would be 2, not minus 2, and then multiplied by the length of V. An example, let's put it here. Example, if I have my by vector v. Say this is 1, 2, and c is equal minus 5. Right, then the length of minus 5 v, this is equal to minus 5 squared times 1 squared plus minus 5 squared times 2 squared, and this is equal to 5, because when we square we get 25, and that comes out 1 squared plus 2 squared, and this is equal to 5 times the length of v. Alright. Now, we define a unit vector v is, oh, let's call it u to be suggestive. U is a unit vector in Rn if the length of u is 1. Now it turns out that you can always scale any vector to make it into a unit vector. So you can multiply a vector by a number so that the resulting vector has length 1. And this can be easily seen from the previous formula. So remember that we had CV equal CV, right? And suppose we want to make this 1. So I want to choose a number so that this is 1. I can assume that C is positive. So then this is equal simply CV. Okay? And I want this to be 1. So assume this is 1. That tells you that C, this number, C, is equal 1 over V. So if you multiply the vector by the reciprocal of its length, you will get a vector of length 1. U, which is V divided by its length, this is a vector. Don't confuse with the ratio as being two numbers or something. This is a number, but this is a vector. So it is more appropriate probably to write V times, so the length of V multiplied by V. So, but then maybe it's visually more appealing to and suggestive to write this way. So you're dividing a vector by its length. This U has length 1. So the length of U is 1. And you can remember this formula because it is useful. U is V unit vector in the pointing in the same direction as V. for example, if I take a vector like this, say this is 3 and this is 1, yeah, so this is my v, then the length of v is the square root of 9 plus 1, which is square root of 10. So if I divide my v by square root of 10, so 1 v square root of 10, this is equal to 1 divided by square root of 10, 3 divided by square root of 10, and then if I compute the length of this vector u, I will get 1/10 plus 9/10, and this is square root of 1, which is 1. And as you can see, this vector u will be pointing in the same direction. So this is u, and it has length 1. Now next, how do we compute the distance between arbitrary 2 points on R2, right? Well, suppose these are your points, and we want to compute this distance. Vectors allow you to do this more elegantly than you might have done otherwise. If you have if you join these points to the origin, and you assume that you're given two vectors, so you're given v1 and v2, alright? This vector itself, you can think of this as a vector which is the difference of the two. So this v, if I want so v is equal v1 minus v2. Yeah, so it will not be quite this vector, but it will be a vector that is parallel to this line, and it has the same length. So this will be v1 minus v2. Because if I add v2 to this vector by the parallelogram rule, right? So so if I add v2, I get v1. Let me use a colored chalk. So I have this vector, right? And if I want to add to this vector, I add v2, open parentheses, I get v1, which coincides with the parallelogram rule. But on the other hand, this vector is the parallel translation of this line segment. You just move this segment to the origin. So it has the same length, which means that if I want to compute the length between any two points, I use these vectors, I subtract them, and then I compute the length of that vector. So this is v1, v2. The distance between these 2 points will be given by the length of that vector. So let's do an example. Let's say this is v2 is 6 and 2, and V1 is, I don't know, 7. No, this is 2 and 6. 2, 6, and this is say 7 and 3. Alright, so then V1 minus V2, it doesn't really matter in which order you subtract the vectors, because for the purposes of the length, it will not matter if you subtract V2 from V1 or V1 from V2. But let's do it in this order. Then you get 7 minus 2 and 3 minus 6. So this vector is 5 minus 3. Okay, 5 minus 3. And then we compute the length. V1 minus V2 is equal square root of 5 squared plus minus 3 squared. And this is equal to 25 plus 9. And what you end up with is 34. Okay, so the length of this line segment is square root of 34, which is, well, it's somewhere between 5 and 6. So now extending this to arbitrary dimensions, suppose you are given two vectors, V and W in Rn, the distance between, well, it's better to do it this way, just not in terms of vectors, but let's do in terms of coordinates. So suppose you are given x1, x2, xn. So there is a point in Rn which you also can think as a vector, and then you are given y1, yn, two vectors or points in Rn, and then the distance between them these 2 points is square root of x1 minus y1 squared plus xn minus yn squared. Well, the final concept of this lecture is the concept of orthogonality, which we will be working with for the next few lectures. This is an important notion in linear algebra. Orthogonality. So two vectors V and W in Rn are orthogonal if the dot product is equal to 0. Right, and to abbreviate the notation, one sometimes writes this symbol, which means V is orthogonal to W. Right now, what does this mean in R2? As an example of this concept. So let me take this vector, which is, let's say this is 2, 1. Okay, and then I will take the vector, which one? Let's take this vector. So this vector would be, say, -1 and 2. Okay, so this is my V, and this is W. If I compute the dot product, I will get 2 times -1 plus 2 times 1, and you get -2 plus 2, which is 0. Okay, so but now if you look at the picture, what you notice is that these two vectors form an angle which is 90 degrees. So in some sense, if you want to generalize the concept of an angle to an arbitrary dimension, or at least if you want to say that two vectors form a 90-degree angle, then the dot product can be used to define that notion. Is a small theorem which gives you an alternative way of thinking about orthogonality. Theorem V and W are orthogonal if and only if you compute the length of their sum and you square it, this will be the same as doing computing the lengths of each vector and then adding their squares. So if this is true, then they are orthogonal. Now, why? The reason is really simple here. Let me give you the proof. What you need to do is to think about this quantity, or go back to the definition and look what this quantity is, right? So what is it? Well, the length of, so you have, in general, the length of the vector squared is really the dot product, because the length was defined as the square root of the dot product. So now what we have here is V plus W dot product V plus W, right? So this is just V plus W squared is equal to the dot product of the sum. Now we open the parentheses using the properties of dot product that I mentioned, and you get V dot product V plus W dot product W, and then you get V times, so plus V times W plus W times V, which of course the same are the same numbers because this dot product is commutative. So I can write this whole thing as, now this is just this quantity. So what I end up with is v squared plus w squared, the length, plus 2 times v dot product w. And now you see that this is equal to that if and only if this quantity is 0. But this quantity is 0 if and only if it's equivalent to this vector is being orthogonal by definition, because multiplying by 2 doesn't do anything. Alright. Yeah. So I guess a more general statement would be just to rewrite what this is. This is equal, in general, this is equal, when you open the parentheses, is equal to that times v w, the dot product, from which you conclude that this dot product is 0 if and only if this is equal to this. Now again, I want to draw a picture of what this means in R2. So suppose we're in R2, and let's take the old example. So we have these two vectors that are that form 90 degrees. Okay, so then their sum will be the diagonal. Okay, and what it amounts to, the previous theorem, is the Pythagorean theorem, because the angle being 90 degrees means that this angle is also 90 degrees, and this is 90 degrees. So then the length of this side plus the length of this side squared is equal to the length of the hypotenuse squared, if and only if the angle is 90 degrees. Otherwise it's not true. Alright. My picture is a bit crooked, but you can draw your own picture. This should be slightly, yeah. Now, one final example for this lecture. Example. Suppose V1 is given as 2 minus 1, 5 minus 2. V2 is 3, 2, minus 4 is 0. And V3 is 2, 9, 6, 4. And the question is, determine if any pair among V1, V2, V3 is orthogonal. Well, explicitly this means we need to compute V1 and V2, and then V1 and V3, and then V2 and V3, and check if any of those dot products or inner product is 0. So this is equal 2 times 3 plus minus 1 times 2 plus 5 times minus 4 plus minus 2 times 0. So that is equal, let me put it here, 6 minus 2 minus 20. So this is definitely not 0. So the first two vectors are not orthogonal. Then we compute v1 and v3. You get 2 times 2 plus minus 9 times 9 plus 5 times 6 plus minus 2 times 4. And here you get 4 minus 9 plus 30 minus 8. And again, this is not 0. So v1 is not orthogonal to v3. And finally, we compute, so now this is v2, v3. We get 3 times 2 plus 2 times 9, then minus 4 times 6, and then you have 0 times 4. Let me skip it. Well, let me write it just to be precise. And then I have 6 plus 18, and then minus 24. And this is 0. So v2 is orthogonal to v3, and the other two are not orthogonal. That's the conclusion. All right. So this is all for this section.